let's go through Activity 8. So the dataset that we're going to be working with is the birth weight dataset, which was created to study the potential effects of a mother smoking on her newborn infant's baby weight. So we'll read in the data file and we'll call it baby here. And what we're going to be looking at is, in particular, the column titled smoking. Now, this is a categorical variable with two levels, never and now, which keeps track of whether or not the mother is currently smoking or has never smoked, basically during pregnancy here. All right, so question 1 asks us to determine which level, now or never, is the reference level. We know that when we interpret p-values, when we interpret coefficients, everything's done with respect to what's going on with the reference level, so it's important to identify which it is. Now, R has the convention that whatever comes first alphabetically is the reference level, and so looking at these two levels, we see that never is the reference level because it is first alphabetically. So when we interpret coefficients, when we interpret p-values, all these things will be with respect to mothers that have never smoked. All right, question 2a asks us to fit a simple linear regression predicting birth weight from only smoking. So let's go ahead and name this model M, predicting birth weight from smoking in the baby data frame. And if we run this and look at a summary of the model, then we can learn something interesting. So one thing that we know is that the coefficient of a indicator variable representing a categorical variable tells us the difference in the average value of y between that level and the reference level. Now, we only have two levels here, so it's going to be the difference in average birth weights between smoking mothers and non-smoking mothers, after accounting for all the other predictors in the model. Now, in this case, since there's only one predictor in the model, the coefficient is just straight up telling us the difference in average birth weights between mothers who smoked and mothers who didn't smoke. And so what we see is that the coefficient of smoking now is minus 271. The units of birth weight are in grams, and so this is telling us that the difference in average birth weights between smokers and non-smokers is 271 grams. Since it's negative, the mothers who are smoking now have that average birth weight that is 271 grams less than mothers who have never smoked. So, all right, let's answer this question here. So, do babies born to smokers or to non-smokers have the lower average birth weight, and by how much? We see that babies born to smokers, the smoking now level, have an average birth weight of 271.77 grams lower than the average birth weight of babies born to non-smokers. All right, so that feels like a pretty big difference and it's worth investigating here. All right, we could actually come up with this answer here, the difference in average birth weights, by approaching this problem with a different angle. We know that the command associate, when we have one quantitative and one categorical variable, will either compare medians or averages of the value of y between the different levels. And so let's just run associate so that we can see that we can get the exact same answer out using this other command if we wanted to approach this differently. So associate birth weight twiddle smoking, data equals baby. We'll make side-by-side box plots showing the distribution of birth weights for the never level and the now level, and it'll also report the averages for both groups, the medians for both groups, the p-values of the difference in averages and medians, etc. What should we be comparing between the two levels? Well, looking at the QQ plot, we see that comparing averages should be an okay thing to do because the points are more or less on the diagonal red line with a little bit of wiggle room that's allowed on the left or the right. So comparing averages is a smart thing. And what we see is that the difference in averages here, 3482 minus 3210, if we just subtract this, we see that's 272, which is that difference in the average birth weights that we found with the simple linear regression here. So same story, just slightly different approach. All right, question 2c asks us whether or not the overall difference in average birth weights between smokers and non-smokers, if it's statistically significant or not. And we're going to come up with the same answer regardless of how we approach the problem. We see that if we use associate to straight up compare the averages, we get an estimated p-value of 0 with a range of 0 to 0.007, so less than 5%. So yes, statistically significant. Also, the coefficient of the indicator variable, smoking now, in the regression model is much less than 5%. So, regardless of the way we approach the problem, we do conclude that this difference in average birth weights is statistically significant. So, the difference in average birth weights is statistically significant. The p-value is less than 5%. So this difference in averages is very unlikely to be produced just by random chance if fundamentally both groups had the same average birth weight. So we have statistical significance. Is this of any practical significance? Is this large or important or interesting? Well, let's just translate this difference into a context that we can really talk about here. So we're not really on metrics, so we should convert this difference in average birth weights into pounds. And so we're seeing a difference in average birth weights of 272 grams. And we're given that 1 pound is about 450 grams. So 272 grams converted into pounds would be about 0.6 pounds. So the difference in averages is about 0.6 pounds. And this is pretty large. If you look up the average birth weight of babies, then you would find that the average birth weight is typically around maybe 7.5 pounds or so. So a difference of 0.6 pounds on average is pretty big and really feels like it is a large difference here. All right, so I would say that yes, it has practical significance as well. So this is definitely worth investigating. So we know that, all right, between mothers, there might be a lot of reasons why we could see variation in birth weights of newborn babies. It might not be due to smoking inherently, but it might be due to other factors. There might be differences in birth weights due to mothers' heights, mothers' weights, mothers' races, etc. So we really, in order to get the purest comparison of the average birth weight between smoking and non-smoking mothers, we should account for other potential lurking variables, other potential reasons why we would expect to see a variation in birth weights between babies. So, for instance, and I'm just putting this out here, maybe another explanation for why we see the difference in average birth weights between mothers and smokers is actually due to differences in gestational periods. Imagine that women who smoke tend to have shorter gestation periods for whatever reason. If you smoke, typically your baby is born sooner than to mothers who don't smoke. Now, one thing that we know is that the longer a baby gestates, the more it's going to weigh. The more the baby is in the mother's womb, the more mass it's going to accumulate just because it's feeding and growing. So if it is the case that, women who smoke tend to give birth earlier than mothers who don't smoke, that would be another plausible explanation for why we would expect to see differences in average birth weights, not due to any inherent kind of danger in smoking, but just due to, differences in gestational periods. So the upshot is that we really need to isolate the association between birth weight and smoking by accounting for other potential lurking variables, other reasons that could otherwise explain the difference in average birth weights here. So let's take one approach. Question 3 asks us to fit a model predicting birth weight from gestational period and smoking. Basically, let's compare babies with equal gestation periods and see if there is any leftover difference in the average birth weights between smoking and non-smoking mothers. All right, so let's go ahead and fit this model, predicting birth weight from gestation plus smoking. That's in the baby data frame here. And what we want to do is we want to fit that model and then look at the results here. So we're going to look at the visualize.model to see what the implicit regression equations are for each of these two levels. We know that behind the scenes, when we do have a linear regression with a categorical variable as a predictor, in effect, a separate regression line gets fit for each level. And so we can visualize them with just visualize model as long as we just have one quantitative predictor. All right, so our model is suggesting that the difference between mothers who never smoke and mothers who do smoke really doesn't go away after we account for gestational periods. What we see is that when we do compare babies with equal gestation periods, let's say 40, we see that the black line is really quite noticeably above the red line. So non-smokers versus smokers. And the way that the model works is that since there's no interactions involved, is that this vertical offset between these implicit regression lines is the same regardless of what gestational period that we're focusing in on. So we see this constant offset in birth weights between babies born to mothers who never smoke versus mothers who do smoke. And so kind of accounting for differences in gestational periods isn't enough to make this difference in average birth weights go away. Regardless of the equal gestational period of the babies we consider, we do see a difference in average birth weights. All right, so let's get a summary of this model here and take a look. All right, so based on the plot, does it look like there is a difference in average birth weights after we account for gestation? Yes, we do see that these implicit regression lines have a noticeable separation. The vertical offset equals the difference in average birth weights after we account for gestation, and that looks to be quite noticeable. So we have obtained the summary of the model, and we can actually write out the overall regression equation and then get the implicit regression equations to make a further comment. So let's write out the overall regression equation. We know we're predicting birth weight here. And the intercept is minus 170. And just going down the list, plus 91 times gestation, minus 240. I'm just going to round to 240 times smoking now. Okay. So if we wanted to recover the implicit regression equation for non-smokers, that is the smoking now equals to 1, quantity here, we can just plug in 1 for smoking now. So I can just literally copy and paste here, and I will do that. And I will just plug in a 1, and I can simplify. Minus 240 times 1 is minus 240, and so that would give me a minus 410. Let's see, let's double check that math. Minus 240. Yeah, I got it right. Plus 91 times gestation. And for the implicit regression equation for smokers, well, that's the reference level. And so smoking now is going to be equal to 0 here. So that's pretty easy to do. I can immediately just simplify this as just birth weight equals to minus 170 plus 91 times gestation. So remember, when we throw in that categorical variable as a predictor, a separate regression line gets fit for each level. Those lines are going to be parallel, like what we see with visualized model, but they're going to have different intercepts. The difference in intercepts is equal to the difference in the average value of y between the levels. And so what we see is that indeed the slope of the implicit regression lines are equal. They're both equal to 91, but we do have a difference in intercepts here. This difference in intercepts is the vertical offset between the lines, and it's telling us the difference in the average birth weights between smokers and non-smokers after we account for gestational period. All right, so let's just review what we're being asked here. We've answered that there does look like there's a difference in average birth weights because those lines are offset from each other. We obtained a summary, and we wrote out the overall regression equation and wrote out the implicit regression equations as well. All right, so let's just follow this up a little bit more. It looks like the difference in average birth weights after accounting for gestation, well, that's just equal to the coefficient of the indicator variable, and that's 240 grams, with smokers having the lower average birth weight. We do see that it's statistically significant as well. So accounting for differences in gestational periods isn't enough to make this difference in average birth weights go away. It does still look like babies born to mothers who smoke have a noticeably lower birth weight than babies born to mothers who don't smoke. All right, so let's continue this analysis. Let's go ahead and examine other potential lurking variables that might be able to explain away this difference in birth weights. Let's find the predictor that's most correlated with birth weight besides gestation. So let's run all correlations in the baby data frame, and the variable of interest here is birth weight, and let's sort it by strength. All right, so it goes from weakest at the top down to strongest at the bottom. Gestation is the variable that's most highly correlated with birth weight. The second most highly correlated variable is mother weight, or mother height. So let's do an investigation with this. All right, so let's fit a model now predicting birth weight from mother height plus smoking from data equals baby here. Maybe, for whatever reason, it could be the case that, say, shorter mothers are more likely to smoke, and it's also the case that shorter mothers tend to give birth to babies that weigh less. If that happens to be the case, that would be another potential reason why we would expect to see differences in average birth weights. It's not necessarily due to smoking, it's just due to the fact that shorter mothers tend to smoke and shorter mothers tend to give birth to lighter babies. It sounds fairly implausible, but maybe that's the case going on. We can let the data kind of tell us whether or not that does look to be the case. So let's fit this model, and let's visualize this model. So what we see is that after accounting for differences in mother's height, we still see a really big difference in average birth weights of babies born to mothers who never smoke, the black line, and mothers who do smoke, the red line. So if we can compare babies born to mothers of the same height, let's say 60 inches here, we do see the really big difference in the average birth weights. So what is this difference? Well, we can look at the summary. And we still see, a difference in averages of about 270 grams here. Okay, so does it look like the difference in average birth weights goes away after accounting for this variable? Why or why not? So the difference in average birth weights remains after accounting for the mother's height. The implicit regression lines still have a very large and noticeable offset from each other. So the difference in average birth weights is about 270 grams when comparing babies born to mothers of the same height. So differences in mother's height isn't enough to explain away the differences in the baby's birth weights. We still have this effect left over that looks like it is due to smoking here, statistically significant. All right, so that's kind of useful for just looking at one variable at a time, but we have a lot of information here. Look at all of these variables that are potential predictors of the baby's birth weight. Maybe after we account for all these other potential factors, the differences in average birth weights in babies born to mothers who do smoke and don't smoke will go away. Maybe there's these lurking variables lurking in here that's able to explain this difference. So let's go ahead and fit a model predicting birth weight from everything. We'll use twiddle dot, data equals baby, and let's look at a summary of this model to see what the data suggests. Can we explain the differences in the birth weights that we see due to smoking versus non-smoking mothers based on maybe some other potential lurking variables? The mother's race, the mother's education, the mother's height, weight, and same characteristics for the father. Okay, so when we look at the coefficient of smoking now, it's telling us something actually really quite special here. So basically, we're assuming otherwise identical individuals, so essentially babies born to otherwise identical mothers and fathers. Mothers of the same race, mothers of the same mothers of the same age, educational level, height, weight, and the babies have the same characteristics for the fathers, the same father's race, age, education, height, and weight here. So basically, we're comparing babies born to parents that are essentially otherwise identical in terms of educational status, race, physical characteristics. So we're basically comparing babies as identical as we can make them as possible. The only difference now is whether or not the mother does or doesn't smoke. That's what the coefficient of smoking now is telling us. And what do we see is that we still see a pretty big difference in the average birth weights here. So what is the difference in average birth weights between otherwise identical babies? The difference in averages is 230 grams. It's negative, so the babies born to mothers who do smoke are on average 230 grams less than babies born to mothers who don't smoke. So babies born to mothers who smoke are on average 230 grams less than babies born to mothers who don't smoke, all other factors being equal. In other words, the mother, father, education, race, height, weight, and age. All right, is the difference statistically significant? Yes, the p-value is much less than 5%. Statistically significant with the p-value being much less than 5%. Is this difference large? Does it have any practical importance? Yeah, it does. 230 grams is a pretty big deal. Remember, the number of grams in a pound was something like, it's up here, 450 grams here, so we're talking about 230 out of, gosh, my memory's awful, already forgot it, out of 450. So we're talking about a difference of about half a pound here. So smoking looks like it makes about half a pound difference in a baby's birth weight when we compare otherwise identical babies here. This is a difference of about half a pound, and this is quite large. All right, so we've done our best now to compare the average birth weights of babies born to smokers versus non-smokers. We know there's a lot of reasons why we might expect to see a variation in birth weights of babies born to different mothers. There might be differences due to mother's height, age, weight, educational levels, race, and same with the father. And by throwing in all those other factors into the multiple regression model and looking at the coefficient of smoking now, we're able to essentially compare otherwise identical babies born to mothers with the same race, with the same education, with the same height, weight, age, and same for the father here. And the only difference that is really going to be differing between babies here is whether or not the mother smoked or didn't smoke. So things that are still left unaccounted for are differences in diet, maybe mother's exercise level. So there are still lurking variables involved, but based on all the information we have available to us, it does look like there's a pretty noticeable difference in the average birth weights born to babies from smoking mothers versus non-smoking mothers. All right, question 6 now asks us to do a further investigation. There's some suspicion that poorly educated women give birth to unhealthier and lighter babies. Poorly educated women don't necessarily have the tools and wherewithal to, have the correct diet and do all the right things you're supposed to do when pregnant. And so, all right, let's investigate this. So the first line of analysis, or the first line of code here, kind of shows you that we do see a statistically significant in the average birth weights of babies born to mothers with different educational levels. So if we look at the values of mother education, we have 3 different levels: below a high school education, college education, and a high school education. These first 2 lines of code here basically says that there is a statistically significant difference in average birth weights between these 3 levels. Now, it doesn't tell us which levels are different, it just says that there is some difference. So it does look like a mother's education does have some sort of connection to the birth weight of the baby. All right, so that's pretty interesting here. However, we can't simply just compare the birth weights of babies for each level of education without really taking into account the possibility that there are lurking variables. We've just seen that, all right, whether or not a mother smokes does seem to be connected to the birth weight of the baby, and there's also some sort of an association between smoking and education. Typically, people who are more poorly educated have a higher chance of smoking. So maybe this difference in averages that we see between the levels of education can be explained just by smoking. Women that have poor education tend to smoke more often, and maybe that's why we see the differences in average birth weights here. All right, so let's look at the drop 1 command applied to our model predicting birth weight from all the predictors to see if we do see any leftover differences in the average birth weights between the levels of education after we account for all the other variables in the data. So let's just go ahead and just do drop 1 on that model where we fit or predicted birth weight from everything. So we'll run the drop one command. And what we want to focus in on is the variable mother education. It's represented by two indicator variables because we have three levels. And what do we say here? Do we have a statistically significant difference in average birth weights between the three levels of mother education after accounting for everything else in the model? Well, no, we don't, actually. It looks like that we're able to explain away this difference in the average birth weights between the three levels of education once we take into account differences in the mother's race, age, height, weight, and the same characteristics for the father, and whether or not the mother smokes. All right, so is there any difference in average birth weights between levels of education after accounting for the other information in the data set? No. The p-value of mother education is 0.119, bigger than 5%. This implies that after we account for the other information in the data, i.e. compare otherwise identical babies who differ only in terms of the mother's education, we do not see a statistically significant difference in birth weights between the three levels of education. So basically, if we restrict ourselves to comparing otherwise identical babies, babies born to mothers who either do smoke or mothers who don't smoke, and with the same characteristics for the mothers and fathers, and the only difference between these babies are the level of education of the mother, we don't see any more statistically significant differences in the average birth weights here. That difference that we saw just by straight up comparing the averages between the three levels of education kind of goes away after we account for the other variables in the data set. All right, so all this analysis, of course, assumes that the regression model is a reasonable reflection of reality. So is this the case? Were we really allowed to make any of these conclusions? Let's check this regression and see if this analysis is decent. Do the assumptions hold up? So the first thing we look at are the statistical tests. If we pass them, we're good to go. If we fail them, since we have so many data points here, well, we need to do those visual checks. So what do we see? Well, we pass the test for equal spread. The p-value is bigger than 5%. We fail the test of normality, so we'll have to check the QQ plot. And looking at the p-values of the linearity test for the individual predictors, actually the only one that we fail is gestation. So we'll look for any sort of leftover curvature in the residuals plots. All right, so making this window quite a bit bigger, we look at this residuals plot. Do we see any leftover curvature? No, not at all. It looks like the band of residuals is pretty nice and flat here. Do we see any systematic departure from normality of the residuals? No, this QQ plot looks actually pretty amazing here. Almost all the points are inside the upper and lower dotted bands, with the exception of just a few points just barely outside on the outskirts here. This is pretty much as good as it's going to get for a linear regression on actual data. All right, well, what about that failure of the linearity with the gestation? Well, if we press return over here, and press back here because I skipped one. Here's the residuals versus gestation. Do we see any curvature in the band of residuals? No, we don't. So whatever failure that the test is picking up on must be fairly small and inconsequential, and it's not going to invalidate our model. So I got to press return a few more times to go through all those other residuals versus predictor plots. But the upshot is that this model is actually really good. It looks like it's a reasonable enough reflection of reality for this analysis to really be pretty good here. So we have equal spread is passed, normality is failed, but the violation looks to be minor and inconsequential since the QQ plot looks great. The gestation predictor fails the test of linearity, but there are no hints of curvature in the residuals plot or in the residuals versus predictor plot for gestation. So overall, this regression looks to be a reasonable reflection of reality. All right, so pretty good. All right, one thing we have also talked about is that not all individuals are created equal when it comes to determining what the regression model looks like. Some have more influence than others. So let's look at the influence plot of this model to see if there are any highly influential babies in terms of determining those coefficients. And we do see a few. We see 4 points here, rows 223, 243, 272, and 553, that contain babies that had more than their fair share of influence over the coefficients of that regression model. All right, now I want you to look at specifically baby 553. So let's look at baby 553 and see if we can determine what makes it unusual. Now, this sometimes works, sometimes doesn't. It could be the case that what makes this baby influential is some really weird combination of predictors, or weird combination of birth weight and predictors here. But very often we can just determine that, hey, this baby had the lowest value or biggest value for maybe some of the predictor variables. So here are this baby's characteristics. If we look at a summary of the baby data frame, we might be able to determine what makes this baby so unusual. All right, so this baby had a birth weight of 1,560 grams, a very, very tiny baby. In fact, that is the baby that weighed the least in the entire data set. It also happened to have the smallest gestational period here. So we do see that, okay, yeah, this baby is a very unusual baby for this data set. It had the smallest gestational period, had the smallest birth weight. It's highly influential because it's so different than the rest of the babies. But it's a valid observation. There's nothing wrong with it, so we definitely leave it in the data set here. But we've been able to identify, just based on these simple summary statistics, what made it so odd. So this baby had the smallest gestational period and the lowest birth weight here. So in this case, we were able to identify what made this baby so odd. It just happened to have, it was born really premature, essentially. All right, so that's our analysis of the birth weight data set. Now let's move into the TIPS data set and get a little bit more practice working with categorical variables. All right, once again, let's focus in on kind of tables where they were seated in the smoking section versus non-smoking section. The theme of this activity is, hey, how do smokers and non-smokers differ here? So let's fit a model predicting tip percentage based on smoker from this TIPS data set. So if we do this and then look at a summary, since there are no other predictors in the model, then the coefficient of the indicator variable for smoker is telling us the difference in the average tip percentages between tables seated in the smoking area versus tables seated in the non-smoking area. And what we see is that the difference is 0.3884 percentage points. That's the units of y here. And we see that since the indicator variable is equal to 1 for tables in the smoking section, on average, tables in the smoking section leave a tip percentage that's 0.3884 percentage points higher than tables seated in the non-smoking section. However, the p-value of the indicator variable is bigger than 5%, so this difference is not statistically significant. So straight up comparing the average tip percentages for tables in the smoking section versus non-smoking section, we don't see any sort of difference in average tip percentages here. All right, however, we've learned that, sometimes the association between variables can be buried or essentially covered up by much stronger associations, kind of like you can't see the light from stars in the daytime because the light from the sun is so overpowering that it washes it out. So it may be the case that the association between tip percentage and, what type of table you were seated at is only apparent after we account for other lurking variables here. So let's fit a more sophisticated model. Let's try to predict the tip percentage based on the bill amount and also where the table was seated, smoking section or non-smoking section. So we'll run this, and then we'll get a summary of this model, and then we'll also visualize the model. We know that when we have a categorical predictor, basically we get a separate regression line for each level. Those lines will be parallel to one another, but they'll have different intercepts. All right, so here's the relationship between tip percentage and bill amount. It's negative. The higher the bill is, the smaller the tip percentage is on average here. And we do see a small vertical offset between the lines here. Smoking yes is the red line, smoking no is the black line. So it looks like when we restrict ourselves to identical bill amounts, say 30, it does look like smokers leave on average a slightly higher tip percentage than non-smokers. So is this difference statistically significant? No, it's not. The p-value is bigger than 5%, and so even after we account for differences in bill amounts, we don't see any leftover difference in averages between tables seated in the smoking section versus non-smoking section. So we say no, the p-value of smoker yes is 0.32, bigger than 5%. All right, well, let's fit an even more sophisticated model. Let's predict tip percentage from all the variables in the data set using twiddle dot here and see what we can see. All right, so let's get a summary of the model. All right, so now when we look at the coefficient of smoker yes, this is telling us something very specific. It's basically telling us that when we compare two parties that are otherwise identical, meaning they had the same overall bill amount, they left the same overall tip, they were paid by the same gender, it was on the same day, it was at the same time of day, and the same party size, what we see is that the difference in average tip percentages between tables seated in the smoking section versus non-smoking section is 1.65 percentage points. And what we see is that difference is now statistically significant. So it looks like, doing a more thorough analysis, there does look to be a statistically significant difference in average tip percentages left by tables in the smoking section versus non-smoking section. But we had to really dig to see this difference in averages. We basically needed to compare otherwise identical parties here that were basically dining in the same day, same time of day, the same party size, same bill amount, etc. here. All right, so what do we see here? After accounting for all the information available to us, who leaves the higher tip percentages? Well, smokers leave a tip percentage that is on average 1.65 percentage points higher than non-smokers. So this difference is statistically significant. Okay, question 4. A now asked us to fit a model predicting bill amount, not tip percentage, from party size and weekday. Maybe people spend more on certain days of the week versus other days of the week here. That's kind of interesting to look at. So let's see if people do, spend more on some days of the week versus other days of the week. Now, one thing that we know is that the bill amount is going to depend on party size. More people in your party, the more money is going to be spent. So we definitely need to account for differences in party size before really comparing the average value of bill between days of the week. So let's do this. Party size plus weekday. Data equals tips. Nice. Let's look at a summary, and let's just for good measure also visualize this model here. So, boom. What we see is that the implicit regression lines, once again, they're parallel to one another. That's always going to happen when there's no interactions. And we see that the blue line here, Thursday, is the lowest amount, whereas the red line, Saturday, is the highest amount. So it looks like, on average, after we account for party size, people spend the least amount on Thursdays and the most amount on Saturdays, on the weekend. Maybe they're ordering drinks, they don't have to go to work on Sunday, so they're out having a good time. All right, so write out the implicit regression equations for Friday and for Thursday, rounding the coefficients the first digit after the decimal place. So, all right, we have the overall regression equation. How do we do this? We say that bill amount is equal to the intercept, basically 5.5 plus 5.6 party size, plus 1.0 weekday Saturday plus 0.2 weekday Sunday minus 1.4 weekday Thursday. So if we want implicit regression equations, we always start out with the overall regression equation, and then we plug in the relevant values for the indicator variables. So if we want the implicit regression equation for Friday, all right, well, weekday Saturday will be equal to 0, weekday Sunday will be equal to 0, weekday Thursday will be equal to 0 as well. Friday is the value that comes first. Alphabetically, it's the reference level. All indicator variables are equal to 0 for that. So this one's really easy. Bill equals 5.5 plus 5.6 times party size. All right, well, what about for Thursday? Well, weekday Saturday is 0, weekday Sunday is 0, weekday Thursday is equal to 1. So basically, we'll be taking that 5.5 and subtracting off 1.4 times 1 here. So that's going to be equal to 4.1 plus 5.6 times party size. Notice both these lines are parallel to one another. They have the same slope, like what we see over here. They have different intercepts. The difference in intercepts is cluing us in to the difference in the average bill amount between these 2 days of the week. All right, so successfully done that. Among equally sized parties, what is the difference in average bill amount between Sunday and Friday, between Thursday and Sunday? Well, we can get these by looking at the coefficients of the indicator variables. So between Sunday and Friday, well, since Friday is the reference level, the coefficient of the indicator variable for Sunday is telling us that difference. So Sunday versus Friday is the coefficient of weekday Sunday, since Friday is the reference level. So the difference in average bill amounts is 16 cents. All right, not all that much. And since it's positive, we have this, that Sunday is slightly higher than Friday. All right, what about between Thursday and Saturday? Well, because neither of these are the reference level, we need to subtract the two coefficients to get the difference in average values. So Thursday versus Sunday, we have that is minus 1.4, the coefficient for Thursday, minus 0.2, which is minus 1.6. So the difference in coefficients. And since this is negative, Thursday minus Sunday being a negative value must mean Sunday is actually bigger. So Sunday's a little bit larger. $1.6 on average higher. All right, after accounting for size of the party, on which day is the average bill the largest, the smallest? Well, we can look at the implicit regression equations to answer this. So based on visualize model, we see that Thursday is the lowest and that Saturday is the highest. How else could we got this information? Well, actually just by looking at the coefficients themselves. So these coefficients are all with respect to the reference level. So with respect to Friday, Saturdays is about $1 more than Fridays. Sundays is about 20 cents more than Fridays. Thursdays about $1.4 less than Fridays. So clearly Saturday is the highest and Thursday is going to be the lowest. Same thing that we get out from these regression equations. So also from the coefficients of the indicator variables, we see that Saturday is the most positive, so it is the highest, and Thursday is the most negative, so it is the lowest. Now, if all of these were negative, that would have implied that Friday was the highest here, because all of those average bill amounts would have been less than Friday here. All right, finally, among equal-sized parties, is the difference in average bill amounts among days statistically significant? So we do see a difference in average bill amounts between these 4 days of the week, and we want to make a comment on whether or not this difference is statistically significant, or if we would have expected to have seen this large of a difference just by random chance, just from the act of collecting data here. Now, these p-values here don't actually tell us what we want to know, because remember, everything is done with respect to the reference level. It's basically telling us that there's no statistically significant difference between Friday and Saturday, between Sunday and Friday, or between Thursday and Friday, because all of these p-values are bigger than 5%. But it's not telling us if there's any difference overall. It's not comparing, say, Saturday and Thursday directly. So what we need to do is that partial f-test that we can do with drop 1. And we'll look for weekday, 3 indicator variables here. We see the p-value is actually bigger than 5%. So the p-value is 0.2539, bigger than 5%. So our conclusion is that there is no statistically significant difference in average bill amounts between days of the week after we account for party size. So the difference in average bill amounts is not statistically significant after we account for differences in party size. All right, there we go.